Hey there, folks. Root Beer here, looking at question 13 on the year 2010-2011 Alberta contest, Alberta math contest. The edges DA, DB, and DC of a tetrahedron ABCD, are perpendicular to one another. Well, that's interesting. What would that look like? Because usually when I draw a tetrahedron, I draw something like this. You're not going to get perpendicular that way. Each side has to be a triangle. And a triangle can have at most 190 degrees. So we're going to have those 90 degrees separated into 3 triangles. My perspective's off here. Let's do something like this. A, B, C, D, or no, it's D that's got the. Oh no, I do have D. Okay. For a second there, I thought I put A. All right, so there's my tetrahedron. They're perpendicular to each other. The length of DA is 1. Length of DB and DC are 2. The radius in centimeters of the sphere passing through all the points is. Ooh. Okay, that's an interesting question. So this is 1, this is 2, this is 2. Okay. So it's a 3D geometry question. I just want to make sure I got those lengths right. Yeah, DA is the one that's 1. So a sphere. Now, if a sphere hits these points, notice that, for example, A, C, and D lie on a triangle. So if we were to sort of turn the thing slightly, so we're just looking at it on the side, and so B and D are sort of lined up to coincide. We look at our sphere that's passing through all our points. On the side, the sphere is going to look like a circle for this triangle here with legs 2 and 1. Right? And so now this circle could, so if I imagine a sphere here, this circle could be a very small circle. It's not necessarily going to be the circle passing through the center. In fact, it shouldn't be. The center should be, somewhere inside the tetrahedron, I would imagine. But I can get a diameter for this circle. I don't know how that would necessarily help, though. So usually with a 3D geometry question, I turn things on sides and look at various side views. And so if we looked top down, for example, we would get A looks like it's on top of D. You get 2, 2, and the circle passes through these as well. And then if you looked at the other side, you'd get A, B, and C. And you'd get 1 and 2 again. But how these circles might help me figure out the radius. Well, D is on every single one of these circles. Right? D is always the point in the corner. I think it's a good idea to focus on D. And maybe its relationship to the center of the sphere. Because we want the radius of the sphere. And it looks like we should be able to get it exactly, or there's the chance that we can't compute it at all. Well, not that we can't compute it, that we won't get one of these answers. Oh, root 5 plus 1 over 2 looks attractive. I like the golden ratio when I see it. I'm sure someone who was a lot more versed in circumspheres and 3D geometry formulas would know how to work with a right tetrahedron and get a formula for the radius. Sadly, I am not such a person. But we can get, so 2 root 2 for that radius, root 5 for this radius, root 5 for this radius. So we know at least there is a circle whose diameter is 2 root 2, and therefore the radius of this circle is at least root 2. So can we cancel out anything that isn't root 2? Root 2 is about 1.4. That's more than it, that's more than it, that's more than it. That's 1.6180333989 or something like that. So that's more than it. So, nope, that didn't narrow anything down. That's okay. It was worth a shot. Now, both of these have radius root 5 over 2. Let's see if we can draw the sphere in here a little bit. And we'll put D on here. So D is part of one circle that does this. Part of another circle that does this. It's part of a third circle that does this. Now, the centers of these circles, when you look at a sphere, my spheres are becoming increasingly more frantically drawn, but the center of any of these circles will be on the diameter, passing right through the center. So, if I look at two of these circles, perhaps the green one, we look at the green one, if top down from the green one, which is over here, looks like this. And it's so its center is up here, and the red one's center is here. Now they both should be on lines that pass through the center of our shape. Root 5 over 2 here. Root 5 over 2 here with that circle. And they both meet at A. So I would say by symmetry, because it's the same circle, so they should both be the same distance from the center. So they should appear as though so how far over do these appear? Yeah, because then we can sort of say they meet here, and that's a distance what from the side, and then yeah, we should be able to work it from there. Okay, so we have to use, so we'll go with this red circle, or red triangle. 2, 1, root 5, but the center here is going to be, so by each of these halves, root 5 over 2. If we drop a perpendicular, we get a whole bunch of similar triangles. So we're going to have a ratio of 1 to, so we'll have a 1/2 and a 1 and a 1 and a 1/2 here. Okay. So if we're looking at our tetrahedron, and the red side is here. So the center is here. That's on a diameter running through the center of the shape, which we'll say is about here. How far away is that from the center? Well, it's 1/2 above here. And we get by symmetry, the same thing happens with the green triangle on the other side. The center is 1/2 above. And it's on a line going right through. And this center here for the blue triangle on the bottom. Nice little symmetry, so we'll get 1 and 1, and it's on a center. So we have sort of a little box in here with D at one corner, these centers at other corners, and then the center of our circle at the closest corner. So there we go. And I sort of misspoke. These guys should actually meet here, above the center for that one. Or should they? So this is perpendicular to this line, perpendicular to that. I'm worried it might be that the angles might come in on a... No, it's got to be straight above, because the diameter is perpendicular to a certain... Yeah, okay, we're fine. 1, 1. D is back here. These are 1/2. 1, 1, 1/2. 1/2, 1, and 1. 1/2 here. And so the center is here. And so how do you find the area along the, or the length of a diagonal of a prism? So anytime you've got a prism with length, width, and height, and you want to connect opposite sides, it's always the square root of the length squared, the width squared, and the height squared. You can prove this with Pythagorean triangles. Put one across the base, and then you're going to have one along this diagonal with the height. Or it's just a formula you might know from 3D geometry. So the radius, distance from the center to one of the points of the tetrahedron, which is on its surface, is square root of 1 squared plus 1 squared plus 1/2. So that's going to be square root of 2 plus 1/4. That's going to be square root of 9 quarters. So 3/2, which I think was A. Yeah, 3/2 A. There we go. So it took a little bit to sort of process that in my head. I'm not the biggest 3D geometry guy, as I have always said in my videos, but I try and embrace the questions when I see them. And if you are someone who's not a 3D geometry person, feel free to go back, go through it slowly, ask questions down below if you're unsure of my reasoning for anything there. But I think I'm going to move on to question number 14. We'll take a look at that in the following video.